Okay, so this is a tutorial on how to do the power wrench skier problem from Long Kappa. So let's get started here. Let's read the problem first. The figure above, which in this case is below because we were given the picture, shows a 41.4 kilograms skier being pulled up a hill by a motorized gear. The snow that has built up on the skier's skis creates a coefficient of kinetic friction between the skis and the surface of 0.03. The skier pulled up the hill on a 20-degree angle at a constant rate of 2.62 meters per second. How much power must the motorized gear supply? Okay, so going into this, let's do our usual, draw a picture in a free body diagram. Let's consider, so we already have the picture given. So pretty much what I did here is I just wrote down all the forces that are being applied to the person, because that's what we are looking for. We're looking for the forces that are applied to the person in this case. Even though we're looking for the power of the gear, we're not going to use the forces of the gear. In order to use this, we need the force of tension in this case, which is by the gear on the person in this case. All right, and this is at a constant velocity, so I labeled that too. Okay, and if you're wondering what these mean, Ft is basically the tension force, Fg is the force of gravity, Fk is the kinetic friction force, and Fn is the normal force. And this is basically wrote in this scenario. The FBD here we have just drawn, we tilted the axis to fit the needs of the hill, and we just basically have x being that slope up the hill, where Ft is to the right and Fk is to the left. And then Fn is the normal force pushed up from the person and is also corresponding to the hill in that regard. And then gravity, of course, being down by a certain angle that was up the hill in this case, corresponds to that, with Fg sine being horizontal and then Fg cosine being vertical in this case, relative to the hill. All right. And then defining the event, so we call it E0, which is event 0, being labeled the person is getting pulled up by a motorized gear. So basically the whole thing. Since we only have one event here, we're only going to really need one table full of list of values. You could have more values and variables here, but I really only listed the things we need for this problem. So we were given the mass, gravity, velocity, coefficient of kinetic friction, and theta, and also the net force. So basically filling these in, we can infer the net force is 0 because there's a constant velocity on the slope. And then theta we were given, and everything else we were pretty much given from the problem. I've highlighted it here. All right, so we need all of the forces in this case in order to determine the force of tension. And what we're going to use with force of tension, we're going to use it to do power of tension. Now you're probably thinking, because when I originally did this, power should be 0, but I was thinking total power. I wasn't thinking, because there's no work essentially. I was thinking this work divided by time, even though we weren't given any time. But basically we're not looking for the total power. We're looking for just the power of the gear, if you know what I'm trying to say. So we're just looking for that gear and rather than the total power. And that power is determined by the net force, or not the net force, by the force of tension in this case. All right, so let's see what we're doing. So first, we need to find each of the forces on the person. And to do this, we'll find Fg through the equation mg. And then next, we're going to set up the y component equation for the net force, and this equation should be equal to Fg cosine theta minus the normal force. Then we solve for the normal force. Then we compute the kinetic friction with the formula UK times the normal force. Then we set up the x component equation of the net force, and this should be equal to the force of tension minus force of gravity times sine of theta plus the force of friction, and keep in mind, or kinetic friction, and keep in mind these are in parentheses because this being minus, because these are in opposite directions from the force of tension. Then we got to solve for the force of tension. After that, we can go over here and see that second and finally we can find the power of the motorized gear. We set up the equation for power. And it should equal to the force of tension times velocity times the cosine of theta. And think of it like work. It's not theta like that we were given. We weren't given that 20 degrees for this. That 20 degrees only really applies to the gravity in this case. This applies to the direction which you're traveling, that angle. And then we compute the power of the gear. Okay, so then we get into solving this. So here we found the force of gravity first. We did Fg is equal to mg, which is equal to 41.4 times 9.81, and we should get 406.134 newtons. Okay? And then I decided to set up the equations anyway, just for reference, and so we can use them later. So I did the net force of the x component and y component, and then did their equations here. And I already specified what they were below, so I won't specify too much, but we go quickly to the y component first, because we're going to need that for the normal force. So since the y component of the net force is equal to 0, then we set the normal force equal to the force of gravity times cosine of theta. And in this case, we'll get 381.64 newtons. Okay. Then we plug these values, or this normal force value, in for the kinetic friction. And then multiply 381.64 times 0.03, and we should get 11.45 newtons. All right, so we have all three of those forces. Now we just need force of tension. So now let's apply this the x component of the net force equation over here now. So solve for f of t, since it's 0, the net force of the x component. So solve for f of t, and we should have the equation be equal to Fg sine of theta plus the kinetic friction. Okay, and we should get 406.134 times sine of 20 degrees plus 11.45, which would result to 150.36 newtons. All right, so we did technically the first step now. Now we just got to solve for power. So set up the equation of power. I did power of T because it's the power of the motorized gear, and I'm just going to label it in regards to tension here. So power of T is equal to force of tension times velocity times cosine theta. Plug those values in. The cosine is 0 because we are going in that direction. So it should be 1 in this case, or the cosine is 0 equaling to 1, so that it shouldn't change the value to negative or anything. And then we multiply that by 150.36 times 2.62, and then we get 393.94 watts. All right, now checking this. So we get the net force of the x component being equal to Ft minus Fg sine theta plus the kinetic friction. So we're trying to solve for 0. We're seeing if plugging in both of the net force components would get us 0 equals 0. And yes, it does. If we plug in our values for the force of tension, we get 150.36 minus 406.134 times sine of 20 plus 11.45. We should get 0 equal to 0, roughly, because these are rounded values, so it probably won't equate to that. And for the y component, we get the normal force minus the force of gravity times cosine theta, 381.64 minus 406.134 times this cosine of 20. We should get 0 equals 0. And you're probably wondering, so why didn't we check anything with power? Well, there probably wouldn't be any point checking with power in this case, because we're going to need that force of tension here. And we basically computed this in the last step. So anyway, that's it for the whole problem.